So our next speaker today, Victor Zavala from University of Wisconsin at Madison. He is an assistant professor in chemical and biological engineering, and he got into this area in a little bit of a roundabout way, and hopefully Victor will relay that to us. Victor.
Yeah, thank you very much. So, so thank you for the kind invitation. So I'm a chemical engineer by training, but the area that I specialize in is in systems engineering, an area that people call systems. So it's like high-level view of complex systems. So needless to say, every time that I show up in a new community, I'm the one that knows the least. So this is not exception. I look at the problems at a very high level, and I strongly benefit from interactions from special people that look in specialized fields like yourselves. So today I want to tell you a little bit about this project that we're very thankful for the USDA to be sponsoring. This is part of the Infuse, the Innovations at the Intersection of Food, Water, and Energy program. So this is a working collaboration with a range of people in things precisely that are more related to agriculture. So Dan Noguera works on environmental engineering, Rebecca Larson, KG Kartikeyan, they're agricultural engineers. They work on organic waste management and life cycle assessment for dairy systems and experimental as well. So we're also working with the US EPA and also understanding some of the challenges that they're facing in trying to understand these things. All right, so just a disclaimer, whenever you see an equation, so just close your eyes. Some of them are going to get very heavy. I like to put equations there just for eye candy, but then I forget that not everyone finds this as pleasing as I do. So I'm a systems engineer, so what that means is that we really try to operate in a way that we try to understand complex systems in a universal way. And what we normally find in every one of these applications that we usually face is that the patterns are persistent. Like we're all trying to solve very complex problems, very complex interconnections, and we're really trying to find, ways of understanding these systems. So in my brain, so if you guys think about how infrastructures are connected, like power grid, natural gas, things that, do not relate to this audience at all, right? But this is a very similar way in how interconnections are happening in other types of networks, like metabolic networks. And of course, every system has its own different types of challenges, right? But from a high-level perspective, these things might be actually having some universal principles. So things that we do in our research is we build optimization models. We build optimization models not necessarily just to make things better, as the name suggests, but we really make optimization to try to understand when systems are going to break. Where are the vulnerabilities? And something that is related to this particular conference, right? What are the key aspects in the data that are driving a decision? Sometimes what we find is that as we start changing the data, we perturb the data that is really absolutely making no difference in the decision that we're making. And that has key consequences from a stakeholder standpoint. People try to enter in all these conflicts. They're trying to decide what are they going to do with the data. They're trying to decide what are they going to do with the new system that they're going to try to buy. It turns out that ultimately that is not going to affect. So I'm going to show you some examples of how that actually happens. So we use mathematics and optimization to navigate complexity, understand also the system limits, vulnerabilities, and the key trade-offs. And at the same time, it's precisely try to incorporate data to make decisions. So remember, ultimately, we are collecting all this data because we want to make a decision, right? We want to understand, but ultimately we want to make a decision. And the question is what decision we want to make as we move forward. All right, so now let's get into something that looks more familiar to you, right? So exactly the same diagram that I showed you before, but now in this context. So this is the food, water, energy nexus. This is a way of thinking about the problem. There are different ways of abstracting this problem. So what I want you to think about is that you have, from a very high level perspective, multiple sectors that are interacting in non-obvious ways. Sometimes they're obvious, sometimes they're hidden effects. So we have the agricultural sector, right, that they're trying to produce all these different types of feedstocks. We have the dairy sector, so this is targeted towards the Wisconsin dairy sector. We have the urban sector, which is really the ones that are driving a lot of the demands for different products. As part of the activities of these sectors, right, we're producing different types of products and different types of byproducts and a lot of waste. And one of the things that I'm going to tell you about is how do we deal with this waste, right? So, for example, from the dairy sector, of course, we're producing dairy products as we might expect, but we can also be producing biogas. And if we're clever enough, we can also process manure to try to produce some byproducts like fertilizer, struvite, and funny things like that, right? So these are complex interdependencies between sectors. These are mostly driven by economics and environmental constraints. From a high-level perspective, everything is driven from economics and environmental considerations, right, and regulation. What makes these types of interaction complicated is that there's a lot of product transformations, right? So we have a lot of very complex interconnections here. We're converting different types of things into different types of chemicals and products. And as you might expect, if you are someone at the USDA or you're someone at EPA, which is at the government level, right? And you're trying to identify what are the critical components in this thing, then you are with very few type of tools that will allow you to make a decision, because there's a lot of complexity in these sectors. And this is a very high-level perspective, but of course, as we start opening each one of those Pandora boxes, right, you start digging into more and more problem. So some of the issues, right, that you're interested in is what are the technologies, what is the data that we need to collect to make those the right technology decisions. And also, a lot of the problems that we're facing right now is that there's really no consolidated market, right? So farmers, for example, some of them think of waste as a positive price. Some of them think of waste as a negative price. There's no settled market. So there's no organized market like in the power grid or in the electricity markets. And that is driving a lot of problems into the way we invest in technologies. All right, so let me move forward. So another aspect that makes this type of problem complicated is that it has huge environmental impacts, right? So we're very aware of this. But the problem is that these environmental impacts are localized and they cover multiple scales, right? So this is the phosphorus concentration in the state in Wisconsin. So you see that we have some dark spots there. So of course, those are the areas that are more endangered. But if we open one of those little dots over there, like the Yahara watershed close to Madison, so we see that this is actually a much more complicated landscape, right? And you might expect the amounts of data that you need to collect to be able to just analyze and understand where are going to be the critical aspects in your technology investment that is going to be driving environmental benefits is a significant amount of data. So the problem that we face normally is that environmental impacts are spanning multiple scales. What that means is also that we have many stakeholders, right? We have a lot of farmers that are dispersed in Wisconsin and dispersed all over the country. And if you are someone that is trying to drive technology investment and pushing new technologies that are going to help the phosphorus problem, then you need to decide how do you prioritize, right? How do you break those types of conflicts? And at the same time is how do we construct suitable metrics that map data into actionable information? So this is the problem with life cycle assessment. We get all this data, we don't know what to do with it. How do we push that data into people? People are going to be making the decision, right? How do you translate that data into informative metrics that you want to do? So I think probably it's fair to say that most of the audience, right, in this particular community, right, are very interested in figuring out how do we make improvements at this level, right? How do we reach higher efficiency, higher yields, better quality products? But at the same time, right, like, let's not forget that there are other side products that are coming out of this big sector. So we know that there are consequences related to nutrient leaks and also to methane leaks. And what we know, and most, right, like we're all familiar with this, we can actually process this waste, and there are a lot of technologies around. There's a lot of, so I'm going to get a little bit into that later, but one of the issues that we're facing right now is that we have a lot of technologies, but the data on the performance of those technologies is all over the place. Like if you go and try to understand what is the total amount of biogas that you're going to be getting out of a ton of manure, it's actually a number that has significant variability, right? So if you are someone that is trying to invest in a technology, you're trying to drive technology decisions, that's a big obstacle. So here I'm just showing two potential routes to recover the waste, to try to do something smart with the waste. So you can try to recover some types of fertilizers, or you can try to recover fuels. So fuels can be biogas, liquefied methane, they can be different types of things. So the questions here, the big challenges are we have limited data on technology performance. We also have few data in this space that allows us to map from your space into the technology space. And we know that technology performance depends a lot on the quality of that waste, right? What's in that waste and how the feeding conditions into the animals are actually affecting the quality of the waste. And what is very important, I think, for me to convey this message right now is that any improvement or any big breakthrough technology in this space can really distort completely the technology landscape that you're going to be needing for processing the waste, right? And that's important just to remember that there are interconnections here. So some of the questions that you are also probably interested in this space is, which products are we going to recover? So we've been pushing for biogas for a long time because we know how to do it, but I'm a chemical engineer and I can tell you biogas is not a very high value chemical, right? So from an economic standpoint, this doesn't make most sense. So I'm going to explain why that is the case. And at the same time, which technologies do we need? Are these technologies going to need incentives? Which kind of incentives are we going to be needing in this space? So more complication. So we do not live, the problem here is that we do not live in isolation. So the picture that I sent you originally, that I showed you originally, was showing the different sectors. But at the same time, we need to understand that the big issue with waste that is coming from the agricultural sector is that it's highly distributed. And it is very complicated, and from a logistical standpoint, it's very hard to collect, transport, centralize, process, and then do something smart with it. So logistics become very important, and this becomes very complicated because we have supply chain networks that happen in a regional network, something like the area of Madison, up to the state level. And then we have all these interconnections with other sectors. And I think one important aspect here to remember is that the agricultural sector does not live in isolation. The agricultural sector is being driven by other sectors like energy, like water, by transportation. So all these sectors have to come together at some point to decide exactly what do we want to do and what do we want to accomplish. So precisely what the purpose of this project that we are working on is trying to construct a decision-making framework that we're calling Plasmo, because that's a name that we came up a few years ago, where precisely the key idea with this platform that is probably related to what this audience is probably most interested in is, I want to understand how different sources of data that you guys are generating has a societal impact. What is the societal impact of that data? How is that going to drive a high-level decision in what technologies we're going to be investing in, or what are the environmental consequences or the environmental benefits of that? So that's precisely the goal. We want to understand what is the system-wide social impacts of emerging technologies, and as part of that also data related to those technologies. With that, we want to inform experimental researchers what are the key aspects of the data. So I want to inform what are the data collection efforts, experimental life cycle assessment. We also want to facilitate, through this tool, access to high-performance optimization algorithms and tools. So ultimately, what we want is that anyone in this audience is capable of building a model. We don't want to be doing it for yourself, right, because you are the experts in what you want to accomplish. But we want to provide for you the capabilities to actually run this model without you having to worry too much about it, right? We want to be able to do quickly this type of analysis. And at the same time, the big challenge that we have in developing this tool is that we need this universal way of mathematical way of thinking about the problem, right? So let me just give you an example of how we're doing this and how the data that you are collecting probably can start coming into play. So again, a little bit of math, and this actually not that much. In the next slide I have more, so I'm just a warning. So, everything comes together from a mathematical standpoint through a type of model that we call a supply chain network. This is not different than what Amazon does and solves for delivering your packages in Christmas, right? So it's a very similar type of problem. So here in our framework, we're thinking about different types of aspects in the model that we're putting together. We have supply chain nodes, locations, where these technologies can be sitting, or you have dairy farms, so you have agricultural fields. So there are different types of things that can be placed in different locations. We have a set of products. The challenge that we're facing in a lot of these things, we can have hundreds of products. So there are a lot of different products. We have flows that are flowing from the different parts of the network. Those are transportation flows. We have sources of different types of products, right, in different locations, and we have the sinks or the demands that are coming into play. Now, each one of these little attributes have their own attributes. So, for example, from a technology standpoint, we're thinking about what a certain technology can produce, what types of products they can produce, what is the production cost, what is the yield factors, and what is the capacity. And the yield factors are really what really the data comes into play. This is a measure of efficiency, right? Like how good of a yield you can get. For example, if I put 1 ton of corn into this system, how many cows or milk you can actually produce, right? So this is how you map different types of products in a universal way. All right, so do not worry too much about this, just read the words. So once you create all these aspects of the model, we actually create mathematical representations that try to couple everything together. So for example, what we do is we create balances of products in each one of the nodes in the network. We also incorporate different types of constraints that tell us if a technology is going to be incorporated in a certain location or not, what is going to be the capacity of this thing, what are the capacity limits in transportation, supply and demand, and ultimately what are the costs. And here the costs are very important, right? Because we have different types of costs. We have costs for the consumers. So the consumers are trying to get as much product as possible based on a certain price. We have cost of supply. So you have different types of people that are trying to sell different types of products into the network. And we also have transportation costs, and we have also processing costs. And what is very important for you guys to realize is that the problem here from an optimization standpoint is that you have all these different stakeholders that are trying to maximize their own objective function, right? So this is a game. It's like a game theoretical framework. In optimization, we also like to call this a multi-stakeholder optimization problem. And it's very important to remember, right, that there are all these conflicting aspects. If we're going to be investing in a certain technology, very, very naturally, we're going to be benefiting one stakeholder and then we're going to be affecting another one. There's no perfect equilibrium, right? Someone's going to have to pay the price, right? So what the framework allows you to do is also to take into consideration multiple stakeholders that are coming into play and try to balance the decisions that you make in technology investment from a societal standpoint, right? More math, just don't read it. So what is important is that there are different types of measuring stakeholder satisfaction. Economists have been working on this for many, many, many years, so this is almost trivial for them. But something that I want you to realize is that pleasing multiple stakeholders is very hard. If I ask each one of you your opinion on what is a critical technology for achieving a certain goal, it's very, very likely we're going to have strong disagreements, right? So now when you're going to be making ultimately a decision, like what type of technologies we're going to be installing in Wisconsin to process all this manure, for example, you can achieve different types of objective functions. So you can try to minimize the average dissatisfaction or maximize the average satisfaction of all the stakeholders. That is in colloquial terms what people call the social welfare. So whenever we talk about the social welfare, we're actually maximizing or minimizing for the average, right? Some economists also like another type of welfare that is called the Rawlsian welfare. I call that the Robin Hood welfare, right? So the Robin Hood welfare is really the decision is actually driven by the person that is worst off, right? The person that is going to suffer the most with this. And if you're trying to think about, for example, how do you balance the objective function of a big farmer against a small farmer, right? If you do the average, you're benefiting the large farmer disproportionately, right? So it is very, very important to be careful about how do you decide the right welfare function that you're going to be using. So we're doing research in all different aspects of how do you do this type of thing. So complexity, we have talked about this, but I'm not going to go too much into this. We have optimization algorithms that deal with this complexity. Just to give you an idea of the horrible nature of this problem, right? It is not very hard for us to construct problems that have hundreds to billions of decision variables. Why that is the case? Think about how many farms we have in a given state. Think about how many farmers, how many agricultural fields, and then you're trying to capture all the interconnections between all those players and stakeholders. These are very, very big problems, right? So we are working on techniques that allow you to deal with this level of complexity. And it's all about how do you manage the complexity and aggregation level and disaggregation levels. All right, so enough of like that. So I want to give you just a few examples of how we're using the framework to actually drive some specific types of questions. And just let me see. Always lose track of time. Right. So we are very familiar with biogas. We really want to control these methane leaks that are coming out of the manure, the agricultural fields. Just a little bit of numbers for people that might not be familiar with this. So that we have in the United States around 265 biogas facilities. Well, the total number of CAFOs in Wisconsin, just to give you just a picture for the biogas space within CAFOs. The total number of CAFOs in Wisconsin is 245. The total number of CAFOs in Wisconsin with biogas facilities is just 39. So this is around 16%. So we don't have that many CAFOs that actually have biogas facilities. And Wisconsin is actually one of the leaders in deployments in biogas facilities, as probably you can see from the map here. So we're really far, right? We're really, really far into how much biogas we're actually recovering from this. As a comparison, also you compare the total number of wastewater treatment facilities in the United States that recover biogas is just 10%, right? And this is not an accident, right? This is not that people are not trying to do their best. This is really driven by economics. The problem is that biogas is not the most valuable product that we can recover from waste. So the obstacles that we have here is that precisely biogas is a low-value chemical. So as I was telling you, I'm a chemical engineer, so I can tell you that. The logistical issues, a big issue that we have with waste is that it's highly distributed, it's in different forms, it is highly variable. The quality of that waste is very hard to manage and predict what is going to happen in an anaerobic digester, for example. And definitely political issues, right? So the fact that society does not have a good way of mapping their environmental goals into some actionable economic metric, right? So I think people want to solve the problem, but they don't have a way of expressing that into money or in a tangible value that they might want, right? So what we're currently investigating is alternative types of products that we can produce together with biogas or different from biogas. So my colleague Dan O'Gara is an expert in microbiology, and he's very interested in anaerobic digestion and improved pathways for anaerobic digestion. So one of the things that he tells me, I'm not an expert in this field, but one of his obvious observations was, well, if you think about anaerobic digestion, this is a very complex processing step that involves many different types of processing sub-processes. And as part of these sub-processes, we're actually already producing something that are called volatile fatty acids. So fatty acids are molecules that have a high concentration of carbon compared to biogas. So you're thinking about C6 and C8 types of molecules. So he says, how about we actually try to drive the anaerobic digestion to produce those volatile fatty acids before converting into biogas? And if we can do this in 2 stages, then we can produce 2 products. We can produce the fatty acids and we can produce biogas. And he said, you know what, but I'm still very early in my experimental research. I have no good idea of how big of a yield factor I can give you for these fatty acids. I don't know how much I could produce. Can you do a techno-economic analysis that tells me what will be the yield factors that will actually claim that this is successful or not? Does this even make sense, right? So precisely what we do was to use our framework to help him answer that question, like if this actually make any sense. And people have been doing this in another space in biomass processing from ethanol and things like that, but he was not completely certain that this was actually possible. So we started digging a little bit into the details of this. So just to give you an idea, so just from an economic standpoint, C6 and C8 will make a lot of sense. So you think about the price of I'm sorry, I have to translate this, right? So C6, normally what we're thinking about here is an acid that is called hexanoic acid. C8 is an acid that we call caprylic acid. So these are like kind of the colloquial terms for this type of acids. Just to give an idea, like the value for these chemicals compared to biogas. So C6 has a market price of $2,800 per ton. C8 has a value of $5,000 per ton. So you see that the value is proportional and almost like highly like non-linear, right? It's not actually bigger than linear based on the molecules. And this is because of the energy that goes into producing this thing, right? So this is $5,000 per ton for C8, and you compare this to biogas. Biogas is $110 per ton, right? So you're talking about an order of magnitude difference, right? So this is a significant issue. Another interesting aspect from a logistical standpoint, one of the obstacles with biogas is that it's actually very hard to transport. If you want to transport it, you have to clean it, and you have to clean it to very high concentrations of methane to be able to inject it in a pipeline or try to liquefy it or do something interesting with it. So this goes into a lot of electricity that you might need to actually transport this system, so it goes a lot of transportation expense. So the nice thing about C6 and C8 is that it actually facilitates separation and transportation because it is in liquid form. So you can produce this in liquid form and it's easier to transport. You don't have to capture and clean it as much to be able to transport it. So the key obstacles that we have here is that even my experimental colleague tells me, look, do not expect a miracle. The yield factor for C6 and C8, you're talking about manure, right? You're not talking about a high organic concentration from a waste, right? So you're talking about manure, it's a very raw waste. So I think the best that I can give you is probably 1 or 2% yield factor, very, very small yield factor. Does that even make sense, right? So let's start building the model. So essentially what we did was to build a supply chain model that captures different types of waste. So we have food waste, we have a sludge from wastewater treatment plants, and we also have cow manure, which is over here, sorry. And what we want to decide is if installing these technologies will actually make sense and what will be the economic potential of doing that. So we run the model. So what the model tells us are we can run different types of scenarios. So the model tells us, first of all, what will be the optimal location for different facilities. So if you decide just to install anaerobic digesters, so it is already suggesting what is the optimal location for installing these digesters. It also tells you what type of flows need to be moving around. So you see that there's a lot of movement of a sludge flow, which is essentially coming from the wastewater treatment plants. Of course, there's not much movement of cow manure. This is only a short distances because there's a lot of mass, right? So it's hard to transport. Now, if you decide to install only technologies that recover this caprylic acid and hexanoic acid, so this also suggests a different type of configuration for the system. And here we're assuming that all the C6 and C8 is being centralized in a refinery, hypothetical refinery that we will install in the middle of Wisconsin. So this is why you're seeing all the flows going inside the state, right? So these are three different things. Of course, they do nothing. We can also simulate what happens if we do not do anything, right? And this is when I'm start running out of time and I start freaking out. All right, so we also run a study that tells you, okay, if you were to install these two technologies together, what would be the optimal configuration? So we also understood this. And the real numbers that I think the start of the show is the following. So these are comparison of the profit, the carbon savings from a societal standpoint, and also the social welfare. And what you find is there are some very interesting trade-offs. Anaerobic digestion, production of biogas has a very high environmental benefit. So you're collecting all this methane, you don't leak this into the environment. This is great, but it does not have a positive profit. So this is actually not economically viable without incentives. C6 and C8 turn out that it's profitable even at low yields, but it has limited environmental benefits. And as a result of that, it actually has a negative social welfare because the environmental impacts of it have a higher weight compared to the economic impacts from a carbon cost perspective. So this is not a great idea. It's a great idea from an economic standpoint, not from an environmental standpoint. But the nice thing about these two technologies is that they can be connected together to create a hybrid system. And this hybrid system actually is profitable, has high environmental benefits, and it has a positive social welfare. So the other nice thing about this is that this technology for C6 and C8 always has a positive profit regardless of the biogas price. So if you have a hybrid system, this technology always works regardless of the price of biogas because it has embedded flexibility in it. And the same story for social carbon cost. So this line, what it tells you, right, as you might expect, is that at the current biogas price, if you just want to install biogas and anaerobic digestion, this is not a good idea economically. If the price of biogas, for whatever reason, goes up to $170 per ton, then this is going to become economically possible. So I'll stop here, and I'll let you ask any questions.
There are a couple quick questions for Victor. So how extensible is the model to other things that, like Santiago talked about what they were doing for a company?
Yeah, so that's precisely what we're trying to understand, like how impacts in yields in different, how impacts in yields in different types of sectors can actually be affecting the overall societal impact, could create a societal impact. So it is extensible in that respect.
Okay, well,
Okay,
in
thank you.
terms of time, I think we'll move on to Raluca.